Then it's time to start the session, afternoon session. And I'm a chair of this session, Keisuke Fujii from Osaka University. And the invited talk 3 today is given by the Professor Francesco Buscemi. So let me briefly introduce him. Francesco Buscemi got his PhD in theoretical physics from the University of Padova, Italy in 2006, under the supervision of Professor Dariana. And after postdoc in Tokyo, in my error-sourced project in quantum computing and information, and also Cambridge Statistical Laboratory, since 2009, he is with the Graduate School of Informatics of Nagoya University, where he became full professor in 2019. He serves in the editorial boards of several specialized journals, including recently launched APS journal PLX Quantum. And also in 2018, he was awarded Birkhoff von Neumann Prize by the International Quantum Structure Association for his work on quantum foundation and mathematics. And today, he will talk about statistical test of quantumness from mathematics to technology. Okay, let's get started.
Thank you very much to Keisuke for the introduction, and to the organizers of AQIS for having given me the opportunity to present my work on this topic. So let me share the screen. Okay. So it's fine. You can see it, right? Very good. So today I will be telling you about quantum entanglement and quantumness that actually followed a very nice parable, because it started, actually let me already go to the next slide. It was first noticed as a feature of quantum theory back in 1935 in this very famous paper by Einstein, Podolsky, and Rosen. But at the time, this quantumness feature, quantum entanglement, was seen as a problem, as a spook, the famous thing that caused a spooky action at a distance. But it was later recognized that this phenomenon that was considered to be a kind of a thorn in quantum theory's side turned into quantum theory's most valuable assets. Because now we know that essentially quantum entanglement is the crucial resource to the design and development of quantum technologies. Just think of the use of quantum entanglement in quantum teleportation that has to serve as the repeater point in large-scale quantum computation, or the use of entanglement in quantum cryptography. Without entanglement, essentially, there is no there are no quantum applications, there is no quantum revolution. So it is an important problem to introduce ways in which we can test and possibly benchmark, quantify entanglement, and more generally speaking, super classical behaviors, let's say quantum behaviors, genuinely quantum properties of devices that are typically given as black boxes. So today I will be focusing I would say entirely on statistical tests of quantumness. Of course, there are possibly many ways to test the quantumness, the quantum character of a given device. For example, one could also come up, actually it is quite important right now, the approach that uses computational complexity, like some computational tasks, to give to a black box and see how the black box behaves against such a problem, computational problem. So today I won't be talking about all these computational tests, so to say, but I will be focusing instead on statistical tests. And in order to clarify what I mean by this, let me start by introducing the most traditional, the oldest, in a sense, way to test quantum entanglement in a laboratory. So this is done by means of so-called quantum tomography. So you have a source that emits a signal, a bipartite signal, and then one can measure locally the two quantum systems that are emitted by the source, and by performing suitable measurements, in the old terminology one would use by measuring a complete quorum of observables on each system, and then by combining the classical outcomes in a classical computer, it is possible to infer, to reconstruct the state of the source. So this is the basic idea used by quantum tomographic reconstructions of bipartite signals. And after you have a reconstruction of the source, like a density matrix, basically, that describes the source, it is possible to compute how likely it is that the source is actually emitting entangled signals. This technique goes under the broad name of entanglement witnessing. So usually when people speak about entanglement witnesses, they are referring to a method like this. So essentially you are doing a sort of tomographic reconstruction of your state, bipartite state, and then you are checking whether the density matrix that you reconstructed from the data is likely to be entangled or not. So quantum tomography is a device, a protocol that is nowadays pretty common. And I would say that from the experimental viewpoint is probably the first thing that one can think of when deciding about entanglement of a source, but it comes with some drawbacks. Most notably, quantum tomography requires measurement devices that are fully trusted, perfectly known. In other words, if the measuring devices are not exactly what they think they are, so suppose that they introduce some bias without you knowing about it, then you could be very easily tricked into thinking that your source is emitting entangled signals while it is not, in fact. And so you end up, when using tomographic reconstruction, you end up in a kind of logic circle, logic loop, where in order to characterize an unknown source, you need two measurement devices or a tomographic apparatus that is already characterized and trusted exactly. So then what happens instead if we don't trust the devices, or whether you want to certify that the source is emitting entangled signals? So in this case, then one resorts to Bell tests that were introduced back in the 60s in response to, or as a way to formalize the content of the EPR paper to make it physical, whereas before it was more of a metaphysical problem. And kind of ironically, now Bell tests are used to certify the quantumness of the source. In the sense that now I will not go into the details of a Bell test, but just to say very briefly that if you have some experimental scenario that is able to produce some data, some experimental correlations that violate any Bell inequality, then you must conclude that you are observing some sort of non-classical correlations. There cannot possibly be any classical explanation of the data you are seeing. And so you must conclude that the source, whatever that is emitting, it's emitting something that has correlations stronger than any classical correlation that one can think of. That is to say that if your source is described by quantum theory, you have to conclude that the source is emitting entangled signals. So the what you have here now, it is something that is completely independent of the measuring apparatus that were used to produce this data that then violated the Bell inequality. And so it means that by observing this data, you can be sure up to a very high degree that actually your source is entangled. That is why these kind of tests are nowadays usually called device-independent tests of entanglement, or yeah, let's say entanglement by now, because you don't need to know anything about the measurement devices. I will come back on this point in the next slide, but let's say that given some desiderata are met, you do not need to trust anything about the actual functioning of these devices. Just by looking at the raw data produced in the experiment, you have to conclude that the source is non-classical. But again, when you have a very powerful tool, it comes with some drawbacks. As before, we saw the drawbacks of tomography, and clearly also Bell tests have their pitfalls. In particular, the first thing that we have to make sure is that there is no communication going on between the two branches of the signal. And so usually what people do when they perform a Bell test on an entangled source is to put the two systems that are emitted by the source very far apart in a space-like configuration, so that communication between the two can be ruled out on the basis of spatial relativity. You can just do a careful timing between input and output and see whether a signal could have been exchanged between the two systems or not. But you can understand that this is very complicated, right? Because light is very fast. So you have to put them very far apart, but you need somehow to be able to control in the experiment both arms of the Bell tests. And so you need a very well synchronized team that is working. But not only. Losses in the detectors can be used to cheat. A very hard-headed theoretician, a very, so to say, die-hard hidden variable sort of theoretician could always imagine that in those events where you lost the photon, you lost the signal, there was some communication or some cheating going on. So then actually the violation of the Bell inequality is not due to the entanglement of the source, but to some other forms of cheating. So then you need, in order to combat this loophole, to close this loophole, you need very efficient detectors, which is hard, right? And also another problem with Bell tests is that they set the bar very high. In the test, that it is known that there exist genuinely entangled states that, however, will never be able to violate any Bell inequality. So it means that there is some kind of hidden entanglement there. And you don't want that. You would like your test to be faithful in a way. You wouldn't want to leave or to have too many false negatives. There are, of course, ways around this problem, but they all require additional systems. So you have to perform some sort of concatenated Bell tests. And you can imagine how hard this is. Already a Bell test is quite hard to perform by itself. So you can imagine to perform concatenated Bell tests. And also from the logical viewpoint, again, you are presented with a kind of dilemma, because now it takes entanglement to certify entanglement. So what would you do if you just have one source of entanglement there available for you? So in Bell tests, to summarize, you have three big problems to overcome. One is the need for a space-like configuration. The second problem is the need for very efficient measuring devices. And the third problem is that you need auxiliary system, or a kind of concatenated Bell tests in order to certify any entanglement, all sorts of entanglement, without having this kind of hidden entanglement phenomenon going on. So now a kind of very natural question to consider is whether we can trade in some trust in exchange of more practicality. So we've seen on one hand, we have a very flexible test, which is quantum tomography, but it requires too much knowledge of your measuring apparatus. In a sense, it is too soft of a test. On the other side, you have the strictest possible test, which is a Bell test, but this set the bar quite high. So can we find a kind of sweet spot in between these two extreme situations? And here comes what I called some time ago semiquantum tests. So we go from a Bell test, which is set up in this way. So you have the entangled source, and one system is sent to Alice, the other is sent to Bob, and Alice is given this input X, and she has to reply with output A. Bob is given input Y, and he has to reply with output B. We move to this situation instead, where questions now are encoded themselves on quantum states. So now the question, the input to Alice and the input to Bob will not be just given as they are, written, let's say on a piece of paper, but will be encoded on quantum states. And then by receiving these quantum questions, as before, Alice and Bob will compute a classical answer. So that's why it's called semi-quantum, because questions are encoded on quantum states, where their answers, the outputs are as before in a normal Bell test. These are classical answers. So if you compare these semi-quantum tests with Bell tests and with tomography, what do you have? So with respect to quantum tomography, you have to trust. So imagine that you are the referee and you want to be convinced by someone holding the source that the source is entangled. So as a referee, you need to trust the preparation that you make of the question states. But once the states are prepared, then you're completely fine. Anything else is on the experimentalists. So in a sense, semi-quantum tests are so-called, belong to the part of the literature that goes under the name of measurement device independent quantum test. And this is good because typically the preparation of a state is easier to do than a measurement. It's easier to trust the preparation of a quantum state than it is to, for quantum measurement, simply because if your states are not prepared well enough, you can just go on preparing them. You can do essentially, you can do post-selection on the preparation, whereas you cannot do post-selection in a measurement without introducing loopholes in a test for quantumness, in a statistical test for quantumness. Whereas if you compare semi-quantum tests with Bell tests, so with fully device-independent certification of quantum entanglement, you have now that semiquantum tests are faithful from the start. So you do not need to introduce any concatenated test in order to be able to certify any form of entanglement, even weak ones, but just a, so to say, a vanilla semiquantum test will be able to verify any entangled state, even those that are particularly weakly entangled. So semiquantum tests are faithful, to use this keyword. And then another important feature of semiquantum tests is that they are quite robust. They're robust not only against losses. In a sense, this is built in the fact that they are measurement device independent tests. So everything that happens on the measuring devices should not care the theoretician that reaches the conclusion, that certify the entanglement. So they are robust against losses, but not only. Quite interestingly, semiquantum tests are robust also against classical communication. And this is quite interesting because instead, Bell tests, as we said before, they require no signaling between the two arms of the experiment. In other words, let me tell you with different words, if just Alice or Bob are able to communicate to the other player, then all Bell tests are trivialized. Whereas if we are performing a test of entanglement using semiquantum setup, then Alice and Bob, the two players that hold the two arms of the experiment, are free to consult each other on a classical channel. They can use unlimited classical communication for free. And still, these won't help them cheat the game. In other words, if the source is not emitting an entangled signal to start with, then any amount of classical communication will not help Alice and Bob to exhibit a violation of an inequality that would lead to the conclusion that the state is entangled. So if Alice and Bob are able to win, so to say, a semiquantum test, to violate the inequality that defines a semiquantum test, this violation has to be explained, must be explained by entanglement in the source. So this point, this particular feature of semiquantum tests make them amenable to use in a particular scenario that instead is completely out of reach of usual Bell inequalities. What is this scenario? The scenario is when we are testing the quantum feature of a process. So we want to test, in this case, we want to test the quantumness of an evolution in time. So you can imagine that this evolution represents like some computation task. It can be a memory, it can be something like that, something that evolves. So now you don't have two parties that are separated in a space-like configuration, some Alice and some Bob, but you have one party that is moving in a time-like configuration. So there is Alice now and Alice tomorrow. You see here, there is the line of time now. And now, you know, forbidding communication between Alice now and Alice tomorrow would be equivalent to preventing Alice to keep any memory of what happened to her today, which is an unreasonable requirement. So classical communication cannot be really forbidden when we are testing the quantumness of a process happening in time. And in fact, we know that Bell tests, usual Bell tests, become trivial in this scenario. So if you try to, to turn a Bell test from a space-like configuration into a time-like configuration, and you say, I ask a question to Alice now, then I wait some time, and then I ask another question to Alice tomorrow, and then I check what kind of correlations Alice is able to produce. And then you try to use this correlation to witness, to certify that Alice actually possesses a quantum memory. There is a genuinely quantum system that evolves in time. Then you are presented, you are exactly in the scenario of so-called Leggett-Garg inequalities, and you are facing the problem of the so-called clumsiness loophole of Leggett-Garg inequalities, which exactly amounts to the problem that it is really hard to prevent a system from keeping a memory, right? You cannot force Alice to forget everything that happened to her today before she gives you an answer tomorrow. So in this situation, whenever we are testing for a quantum process, no Bell tests can be possibly considered. But now, then, the fact that semi-quantum tests instead are robust against classical communication comes in handy. Because now it is possible to show that for any process that involves a genuinely quantum memory, there exists a suitable semi-quantum test in time. So let's say like a signaling semi-quantum test that is able to separate this quantum memory from unlimited classical memory. And this would be done as follows, and actually it's been done in experiments by groups in China and Switzerland. You hand Alice a question encoded on a quantum state today, you wait some time, and then you give her another quantum question omega y later on. She has to produce a classical outcome, and then you, the referee, knowing x, y, and b, you are able to compute this correlation, and this correlation will provide you a witness that you can use in order to conclude whether Alice was actually able to store a quantum memory during this time frame that you set for your experiment. So semi-quantum tests are crucial. They're not just useful, they don't just hit a sweet spot in the case of witnessing a quantum process, but they are the thing that you need to witness a quantum process in a scenario like this, because Bell tests won't be helpful. But is this all? Can we move a little bit more upwards in the generalization of the notion of quantumness? So should we stop our quest for quantumness only for bipartite states and quantum memories? No, you can actually have something more general. So you keep the bipartition of the source, and you also add to this bipartition, you add the time evolution, and what you end up with is a bipartite channel with two inputs, A and B, that you can think of them as belonging to two separate parties, say Alice and Bob, that outputs two systems A prime and B prime, that again you can imagine as being in the hands of two separate parties. So we can call this very generic box as a type of quantumness. So I will tell you in the next slide what a type is, but for the time being, just keep in mind that these input and output arrows could be whatever system you like. They could be a quantum system. So then you have a fully bipartite quantum channel. Some of them could be classical systems, some of them could be the trivial system, like the one-dimensional quantum system, which is number one. So when the arrow is not drawn in the picture, then you have to think of it as the trivial system being there. So a channel with no output or a channel with no input. So when you have a type, why we use the name type? This is a bipartite channel, yes, but then you can introduce types in these bipartite channels by dissecting them. You can dissect them in space so that you can consider types as being described by this space-like correlation. So what kind of a system is input by Alice, what kind of system is output at Bob's ends, and so on. But you could also cut a bipartite quantum channel in the time-like dimension. And so then you could ask whether quantum information was propagated in time or whether only classical information was propagated in time, or whether you have classical correlations that synchronize the two arms of the bipartite channel and so on. So you can introduce all these types depending on these dissections of your bipartite box. So for example, using bipartite boxes allows you to provide a unified framework for a lot of resources of quantumness that were considered separately. A bipartite quantum state most certainly is a bipartite box, a box with trivial inputs and two quantum outputs. A no signaling box, like a Popescu-Rolich box, a PR box, is a bipartite box with two classical inputs and two classical outputs. Or you can imagine a steering assemblage. And a steering assemblage is a bipartite box with one classical input, another trivial input. You see there is no arrow here. And then it has another classical output, but now, oh, sorry, but also a quantum output. So a steering assemblage is also a special bipartite channel, and so on. You have quantum teleportage, channel assemblage. You have a lot of scenarios that have been considered recently as resources of quantumness, and you can just look at them as just being bipartite channels, as being particular types of quantumness. But okay, so these were all types defined with respect to the space-like bipartition. So all these boxes here in the slides are typically considered as no signaling resources. So that no input at Alice's end can cause a flow of information to Bob's output and vice versa. But one could also imagine something a bit more general, where instead you're also looking at the bipartition in time. So you cut your channel along the time direction and you put conditions in there. An example of this could be the boxes that represent a programmable measuring device. So what are these objects? Here you have a box with two inputs. You have a quantum input Q and a classical input X. And at the output, you only have one classical output A. And the idea is that this classical input X is used to program a particular POVM on Q. So you see that the POVM that is measured on Q depends on X. So here you have signaling, right? If you want that this box represents a programmable measuring device, you need signaling, right? The classical input needs to carry a signal to the measurement so that this measurement changes depending on the input. So now you might have two different realizations of this thing. One possibility could be that the classical inputs reaches the other system only after a measurement has been performed. In this case, you have that your program X is only able to change the post-processing, the classical post-processing of the output that were obtained by this first measurement here. So these kind of programmable measurements are usually called compatible measurements, because this is indeed a programmable quantum measurement, but you're actually only programming, you're only to program only a classical post-processing of one measurement that is there. So the box is actually doing just one fixed quantum measurement, and the program is only able to change the classical post-processing of this one fixed quantum measurement. So these are usually considered to be weak quantum resources, because you see that you cannot actually be able to change the quantum measurement. Whereas if your classical program is able to reach the system Q before the measurement is done, then this program can actually use to change the POVM genuinely, so that the box can give rise to incompatible measurements, which are important in various scenarios. Like in cryptography, you might want to measure some incompatible measurements in order to keep secrecy, for example. So in quantum theory, we want incompatible measurements. Quantumness here, it's quantumness in time. You see, there is a kind of bipartite structure, because there is the program and the quantum system that undergoes the measurement, but also there is a structure in time, because it depends on when the classical program reaches the quantum system. Depending on this, you can have incompatible measurements or just a box that is able to produce compatible measurements only. But in any case, so however you dissect this type in space on in time, the main message is that semiquantum tests, of course you have to suitably define a semiquantum test, but basically the structure will always be the same. So you have some questions that are encoded on quantum states. So non-classical correlations, space-like and or time-like of any type, can be witnessed by means of a suitably defined semiquantum tests. That is to say, it can be witnessed in a measurement device independent fashion, which is an interesting result by itself, at least with some practical application. If you want to certify that quantum information is actually flowing from one event in space-time to another event in space-time, irrespectively of their causal ordering, you might want to play a semi-quantum test there, because then you don't care about, classical communication being exchanged, or what really matters there. In order to violate a semi-quantum inequality, you really need the flow of information, or at least quantum correlations, if the two arms are space-like separated. But there is also another reason why I got particularly interested in semi-quantum tests, is because of their connection with the theory of statistical comparison in mathematical statistics, in classical mathematical statistics. Why? So until now, we only have been discussing about using semi-quantum tests to certify quantumness. So if you violate an inequality, then you have to conclude that there was some quantum device at work in the laboratory. But this is, in a sense, a kind of, you know, a yes/no question. You want to say something more. You want to be able to compare two quantum devices and say, for example, that there is more quantumness in one than it is in another. And typically, of course, this brings about a partial order only, because quantum devices are multi-parameter objects, and so they don't end up being totally ordered. I mean, if you want to project all of them on the real line, you're going to lose a lot of details of the structure. So the theory of statistical comparison was introduced in mathematical statistics to compare multi-parameter objects like statistical experiments. So statistical experiments are the following thing. So they are mathematical models of some statistical tests that you can do. In others, the story, as it is usually told, is as follows. You have some unknown parameter that you want to estimate, say theta. And theta cannot be accessed directly. You cannot look directly at theta, but you can spy on it by preparing an experiment, which is to say you prepare some physical system from which samples can be drawn, and the distribution of the sample is influenced by theta. In other words, mathematically speaking, a statistical experiment is given by giving a conditional probability distribution of x, which is the sample, given the value of the parameter theta. So it's the basic of all like hypothesis testing problems and so on and so forth. So just let's keep in mind, for the sake of this presentation, that statistical experiments are just conditional probability distribution. And now what it means that we compare statistical experiments. So suppose that you have two possible ways to spy on theta. One is given by P of x given theta, the other is given by Q of y given theta. And now you ask the question, which one is more informative? And here, more informative, of course, I should define it rigorously, but let's say that it means that it yields better values in statistical tests or statistical games, as they were called at that time. And a central result in the theory of statistical comparison, I would say the foundational result of statistical comparison theory, is also called Blackwell-Sherman-Stein theorem, which was developed in these years between 48 and 53, that tells you the following. It tells you that a statistical experiment P is more informative than Q if and only if there exists a stochastic transformation that turns P into Q. So you see that the notion of comparison of the information value of two statistical experiments has been turned into a problem of simulability. Whether you can simulate Q by having access to the samples generated by P. It's statistical sufficiency, in other terms. So now the question is, we are comparing quantum resources, quantum devices here. So can we find out, can we prove a Blackwell theorem for quantum resources? And the answer is yes. So the first result in this direction that I found was for bipartite states. So you can say you have two bipartite states, and then you say, okay, I can violate all Bell inequalities more with this state than with another state. Can you conclude anything about the simulability of the two states? No, you cannot. Or I can say the value of any entanglement witness is higher for this state than for another. I'm not sure even that this question makes any sense. But now if you ask, what is the condition for which one state gives you a stronger violation of another state with respect to any semi-quantum tests? Then the answer for this question is very neatly given in terms of local operation and shared randomness, in the sense that lambda, the source lambda, is better than another source lambda prime if and only if lambda can simulate lambda prime by means of local operation and shared randomness. In formula, it looks as follows. So this is a neat connection between semiquantum tests and simulability of bipartite states. But you can go further. You can consider quantum processes. So now I can tell you, you have two processes, let's say a quantum memory that transforms quantum system A in quantum system A prime, so a channel. It's a quantum channel, a CPTP map from A to A prime, and then you have another CPTP map from B to B prime. So what does it mean that M is able to win more than N with respect to any semi-quantum tests in time? Well, this is equivalent to say that the weaker channel N can be simulated from M by means of a pre-post processing with a classical side channel, which is a kind of quantum comp, to use the name that was introduced by Pavia Group some years ago. So it's a classically correlated quantum comp with a pre-processing, a post-processing, and a classical side channel that helps you synchronizing the two. Again, this is a neat connection between the theory of semi-quantum tests in time and simulability of quantum channels. In formula, you have this. So you have an instrument done at the beginning that produces this outcome I, which is then brought up to the decoding channel, which are all instead CPTP maps now. But also you can do the same for general no signaling types. So now in general, you have a bipartite box, this black box inside. And if you can use this black box inside to simulate another box outside, this blue box outside by means of local operations here, which now are local comms, possibly supplemented by shared randomness, these can be witnessed. Actually, it's equivalent to having the black box being having the black box stronger with respect to all semi-quantum tests than the blue box outside. So again, this connection is pretty clean. And also, well, with types, you can do this you can introduce a cross-type comparison. So you can compare states with Pierre boxes, you can compare a state with a steering assemblage, or you want to ask the question whether you can encode the quantumness of a state in a steering assemblage, or encoding the quantumness of the teleportage in a channel assemblage, or whatever. You can answer all these kind of questions. So you can cross through types freely. You don't have anymore the quantumness of a state or a quantumness of a channel. You just have quantumness of these bipartite types. But again, you can do even something more by looking at the section along the time dimension. And here there is a result about the simulability of programmable measuring devices. So let me wrap up. My time is over. So let me wrap up my talk by listing the main ideas that I would be happy if you take them as final messages. So first of all, we have to keep in mind that the quantumness that we're speaking about now started as a problem of theory. So people were scared of this quantumness, and now instead we are able to harness the power of this spook to make things work for us. And then there are trade-offs when you do statistical tests of quantumness. You have tomography versus Bell tests versus semi-quantum tests. And for some reason, you might be happy with semi-quantum tests. Also because this can be extended from entanglement to memories, so quantumness in time, no signaling types, and even beyond. And then also because there is this nice connection with order theoretic developments like statistical comparison theory, which involves also cross-type comparisons and conversions. And here is a list of references. I would like just to mention co-authors that helped publishing papers: Denis Rosset, Yongchen Liang, Eric Chitamber, my PhD student Wenbin Zhou, David Schmidt, and I thank you for your attention.
Thank you very much for a very nice talk. And now the session is open for the question and comment. And please write down your question in the Q&A box. Or if you raise your hand, then we can unmute you. So we have one question. This question is regarding the semi-quantum test. So in a semi-quantum test in time, can the second question depend on the answer of the first question?
It can, but it need not, right? Because you want the game to be as easy as possible. So let me go back to quickly to the slide of semi-quantum. Is it still shared, the screen? Yes?
Yes.
Do you still see? Okay.
Yes, yes.
So here, right? Actually, you do not need Alice to give you any answer at the beginning. So you do not actually need A. So you just give Alice a quantum question now, you give Alice another quantum question tomorrow, and only then she is required to output a classical output B. So no, you do not need to have any sort of adaptive strategy there.
Okay, is that okay? So, So Kyung Lee. Maybe okay.
See in the chat. Yes, yes. There is answer. Yes, it was enough. Okay, very good.
Yeah. And is there any other question or comment? So we have several minutes. So, okay, so Professor Hayashi have a question. So please unmute Professor Hayashi.
Do I have to do that, or?
I guess
no, we have
already unmuted.
Okay, can I speak? I have one question. So I could not find the relationship between the difference between the your setting and usual self-testing. Could you explain the difference from self-testing?
Oh, well, self-testing is based on a Bell inequality. So you have classical questions and classical answers. So you don't have this tau x and omega y, but you only have x and y. And then self-testing tells you how close you can go to a given pure state, right? So if, for example, like in the usual CHSH inequality, if you know that you can go, you know that you can violate up to the Tirason bound, then you have to conclude that somewhere hidden in your experimental apparatus there was a singlet state, and that the measurements somehow were equivalent to sigma x and sigma y and so on and so forth. So there you are saying you are using the violation of a Bell inequality to get an estimate of how close you can get to that pure state that is extremal for that Bell inequality. Here instead, I would say that it is closer in spirit to entanglement witnesses. Actually, there is a way to turn any entanglement witness into a semi-quantum test. So you are really characterizing the set of separable states. So you are working in the set of states rather than in the set of correlations. I don't know if that helps.
I think in the case of self-testing, we don't have the assumption for the measurement device. We assume that the measurement device and state is independent. We have
Yes.
that weak assumption. But what is your assumption?
So the assumption here is that you know the states that are prepared. So the referee knows tau x and omega y, right? But then so yeah, I mean, self-testing is a fully device-independent test. So it is stronger, right? In a sense, but it comes with the drawbacks of a Bell test. So it means that it cannot be used to witness, for example, you cannot self-test mixed states as far as I am aware. You can only self-test pure states. So if you have a source that is emitting an entangled mixed state, you're out of luck with self-testing.
So what is the assumption? You can assume measurement device. You can trust the measurement device in your setting?
No. Measurement devices are untrusted. So like whatever happens in the experimentalist laboratory, I don't care. As a theoretician, as a referee, I only want these question states to be trusted. So I want to be able to prepare tau x and omega y, and I want to know that the thing that I give to Alice and Bob are actually these two states. But then what Alice and Bob do is completely up to them. I don't care anymore. Once I give them these states, then it's up to them. They can try to cheat with losses. They can try to cheat with classical communication, and still they won't be able to trick me. So I trust the preparations of these question states, which are local states.
Okay, I understand. The state is trusted in your setting. Okay.
Yes, but not the measurement.
Okay, I understand.
Is that okay for Professor Hayashi?
Okay.
Okay, so is there any other question or comment? Okay, if not, then we will finish this session. So let's thank Francesca again for this great talk.
Thank you very much for your attention.
Thank you so much.
Thank you.